Also, I'm gonna be recording these lectures, so if you're in a spot, you can watch this sync live, or you can watch the recordings after, or both, but I encourage being here live for the best experience. You guys may have a different opinion on that later, but, so after class, I will post the recording on Canvas and also my YouTube page. I've got links to that. And I'll also put your homeworks up there. You can expect somewhere in the closed interval from 6 to 10 homeworks probably this semester. And that's it for your grade. Your grade will be based only on homeworks. So let's see what else. I think you all are graduate students. You all should probably, well, most of you, graduate students in training. So you probably all know each other. If you don't, change that, because you all are going to be colleagues for, maybe the rest of your career. So, I encourage you to work together on the homeworks. I think that's a great idea. You can ask me questions, you can work them on yourselves. My only rule is, when you write it down, when you have whatever discussions you have, I want it to come from you. We're supposed to give a statement on AI, artificial intelligence. That's like an oxymoron, isn't it? Because the intelligence is imitating us. So it's actually kind of interesting, because I would encourage caution with artificial intelligence, because this is the real dangerous part of it. It's real hit and miss. And you can be a witness to this, Jared, actually, because when ChatGPT first came out, I asked it some math questions because I am a curious fellow. So this was a while ago. It got them all wrong. But the funny thing about ChatGPT is somebody seems to do a program to be totally cocksure about itself. Oh yeah, here's the answer, and this is blah, 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 blah. And it was just garbage. So somebody said I ought to try it again because it's updated. So I'll tell you the problem that I asked ChatGPT, and this was over the summer, or maybe it was in the spring. Find the smallest prime divisor. I asked ChatGPT this question. This is a classic from number theory, because if you actually get on your horse and just try to go through the prime divisors of this, you start dividing like, just kind of bulldozer it. It'll take a while. The smallest prime divisor of this is 641. And this is kind of a classic number theory problem, because you can use some number theory and to greatly kind of eliminate a lot of stuff and then come to this conclusion fairly quickly. And that's the whole point to it. So I asked ChatGPT this, wondering what it was going to do. My first guess was it was just going to scrape the internet and just tell me the answer. Nope, it didn't. It started dividing. It just went through it. It did it for me. Oh, let's see if it's divisible by 2. Let's see if it's divisible by 3. Let's see if it's divisible by 5. Like that. And then when it divided by 11, it told me it divided imperfectly. This is a number that fits on a handheld calculator, right? And ChatGPT got it wrong. It couldn't even divide by 11. But then Jared, I believe, he marveled at this mistake as well. You asked it to write you some code, right? And actually over the summer, I did the same thing. It wrote the code perfectly, right? I mean, you can bet your bottom dollar I checked it. But so artificial intelligence, be careful, right? Do things for your amusement, that, at least for now. So that's kind of my word of caution here about that. Let's see. And there's something else I was going to bring up, but anyway, so we'll get started here. So, oh, yeah, yes, and here's let me start off by apologizing to anybody that had factorization techniques in algebra number theory with me last year, because there will be some overlap with this, which is somewhat necessary. if you look at the syllabus, I've kind of updated the topics in this. So there will be some things that you see that are similar. I'll try to put a different spin on it. There'll definitely be a little bit less of a number theory, more just kind of pure algebra and less of a number theory factorization kind of thing going on this. There's a lot of topics that I put way too many topics in the syllabus to realistically cover. So if you see anything that you're particularly interested in, just let me know. So let's start off with the basics. Oh, and one more thing, I do post these notes, they will be changed. You can link to the notes now, so I've got them up there, but especially toward the later, at the beginning, we'll probably not change them. As the course goes on, later will. So, definition. I don't know if you say it differently, it's written down. What is a ring? Well, it's basically a place where you can add and multiply, right? So if you consider only the operation of addition, it's an abelian group, such that puts the multiplication plays nicely with the operation addition. Let me be specific on what I mean. So what we have is we have R S plus T equals RS plus RT for all R S T and R two S plus T R is SR plus TR for all RST. And I do want this, I didn't say it, I probably should have said this first, but I want the multiplication to be associative. So that's what it means to be a ring, but in this class, almost without exception. So there's a couple things you can take for a default. So you can assume these two things. Assume by default I'm going to make a couple of nice assumptions, and if I ever want to get out of this territory, I will make it clear that one x y y x for all x y and r. So I will assume my limit is commutative. And number two, I am going to assume, and this may seem like kind of a small thing at first, but this is actually important. There exists I will assume that my links have a multiplicative identity unless I say otherwise. And you know, it's really funny because for years I thought of myself as taking the easy way out because I always considered commutative rings, but actually the real easy way out is with the identity. It is really, it's surprising how awful things can be, even if you remove just the identity. Okay, so this is what a ring is. We will assume commutative with identity by default. So, as is always the case in mathematics, some examples, a ring V is a commutative ring of identity. And one might say that really ring theory is an attempt to generalize Z. Z has very nice properties, as you know. And really, it is sort of a prototype of a place where you can add and multiply. 2Z is a commutative ring without identity. So that's a good example of a ring that has no identity, no multiplicative identity. So another example. Four pairs in M. This is a ring. Let me tell you how multiplication works. This is a ring. Oh, and let me just be transparent on this. What is the multiplicative identity here? Um, right. Okay. Notice so let me, I bring this example up to point out some subtleties here. Notice the set of elements look like N0. It's a subring, right? But there's some subtle things that go on. Notice if you add two things in this form, it's of this form, right? And if you multiply N0 times N0, it's NM0, all this, right? Does this ring have an identity?
Oh, yes.
It is. Well, what's the identity?
So what is your?
Right? But notice, some people would not call this a subring because the identity is different from the one upstairs, right? So we will say S in R is a subring if S is a smaller ring inside R. Right, so it itself is a ring. It's just it's a subset, non-empty subset. It itself is a ring. We say it's an R is a with shared identity. If S has identity and the identity S, the identity R. So in this example, what you have is it's a subring by my definition, and it's a subring with identity, but it's not a subring with shared identity. Any questions? By the way, here's another kind of hobby on this, when you think about rings. Can anybody think of another way to make this a ring in the following sense? Example, let's again take Z sum Z. Order of pairs in M. I'm gonna have my addition rules the same. So AB plus XY is A plus X, B plus Y.
We're going to give it complex multiplication.
Okay, so, yeah, so that's my question is, how can we multiply? So can you be more specific? So my question is, is there another way that I can make this a ring? I have to find another multiplication. Now you see complex multiplication, what do you mean by that?
Question, I have to work out the relations.
It's too complex, right? How about this? Can anybody think of another way?
This is really stupid, but it's countable, so you can just put it in bijection with the integers again.
Oh, okay, yeah.
That's really stupid.
Well, yeah, the problem
I
is,
guess I wouldn't respect addition.
here's another thing. So this is gonna look like I just kind of freaked out. Make that happen. How about that? Huh. Gee, yeah, what's the first thing that you might wonder about?
Actually,
Right, so what might worry you? Right, okay, certainly we've got the abelian group covered. Okay, so one is kosher, right? What about this rule here? I need to think of more letters. So what about this? I'm gonna hate myself for this. What's this? This is our rule here. AB or AX and then AY plus BX, right? And then ST. Right. Okay, so this is AXS. Right? And then this times this, AXT. And then this times this, plus ASY plus. I just kind of shuffle those letters in. Now, on the other hand, let's see. Well, let's see if I can do this reverse engineering this. Right. Well, XS and XY. I hope that's right. This is AXS and this is there an AXT? There is, and there's BSY or is that right? AXT and ASY, good, and then a BSX. Everybody agree with me? and then pull this apart further. Well, that appears to work. Alright, so, and that, to me, that was the big hump, right?
Yeah.
Right, so the distributive part, I'll let you check for yourself. What's, does this have an identity? It's not 1, 1 though, is it? Huh? In this case, if I agree with that, that's an easy check. And what's the magic here? Well, now, if S is then S is a subring with shared identity. Right? I agree with it. Anybody know where I came up with this example?
So you join X mod X squared.
That's essentially what it is. That's the inspiration, well, because if you notice, and I really wish I hadn't did that, but I did. If I look at something like A plus, I'll put my other letters here, SX plus Y, and B plus PX. Right, everybody, since you're in a graduate class in algebra, I'm assuming you've multiplied polynomials before, right? If I have two polynomials, first coefficients A and S, and then B and T for the first two coefficients. If I multiply the polynomial, I get AB plus the linear term is going to be AT plus BS in their entire terms, right? That's exactly where you picked it out, Eric. That's exactly right, because what it is ordered pair times ordered pair, and get the ordered pair here. And essentially what I'm doing is I do polynomial multiplication mod X squared, right? So it wasn't clear that was going to be a ring, but I knew that it was going to turn out. But anyway, this illustrates that with these two operations, we had the same sort of subset being a subring. One had shared identity and one did not. Okay. So more examples. Examples are the heartbeat of math. You know, we beat on students when they're in the proofs course and tell them, because if any of you ever, and some of you will teach a proofs course or had to deal with somebody with proofs, lots of times, especially engineers at recording, think that, you know, proof is to do the first 5 cases, right? Engineer's induction. Right. But even though we pick on them for, you know, saying, well, an example of proof, examples sort of drive everything. Yeah. Well, is a family of things. They can be community or not, entity or not. Then the direct sum of these rings is a ring. And I'll tell you how the operations work. This index set may not be countable, so I'm going to write a typical element of this as, I shouldn't say sequence, I'll call it net. So if I have, let's say Ri, a net of things here, and I add it to Ri prime, Then addition, you do what comes easily to mind. You make the new net by adding things, coordinate by coordinate, if you will. And multiplication. I seem to have totally freaked out here and used the I and anyway, so interchangeably. What do you suppose we want to do here? How do we want to multiply these? Remember, those of you that haven't had class with me, the fundamental rule of mathematics is what? Anybody know?
Whatever's easiest.
What's that?
Do whatever's easiest.
If it ain't easy, don't do it. Right, so let's do the easy first. I thought you well, young Padawan. Okay, you can also do the same thing with the direct product. With multiplication given well, actually, I don't know why I'm writing this, multiplication, and addition, sandwiches. That is just coordinate wise using the operations of ring. And of course, these can be very different structures, if the index set is not finite. If the index set is finite, they're isomorphic. So in particular, by the way, I'm sure that y'all, how many of y'all had 85-10 here? Some of you may have had it somewhere else, whatever. Can you all complete this theorem for me? If you have a commutative ring with identity, it always has a maximal identity. How many of you have heard this theorem before? In fact, there's actually a stronger, better statement of that result that says, right, if you have a commutative ring identity and I walk up to you on the street, just give you any idea, it is contained in a maximal identity. So you can, yeah, it's a Zorn's limit thing. So, or short, actually, I'm gonna call this, S for sum, and goes from P for product. So I'm gonna look at this example really quick, and I'm looking a bit ahead, but I'm assuming that you all know that theorem that I just gave you about maximal ideal, so. Just like this previous example, this is a ring, and so is this one, right? The only difference between these two is everything that lives in this animal has to end in an infinite string of zeros. Whereas this, I get complete freedom. Can somebody, if I was in a logic or analysis class, can anybody tell me what's the first thing that jumps out at you? Something that's different between S and P. I am counting on you to give me a good answer.
This is countable.
This is countable. Countably infinite. This is not. Because actually you can think of this as an arbitrary sequence of zeros and ones, right? And so you can put that in one-to-one correspondence with the interval from 0 to 1 on through the line. So S is a ring, P is a ring. Can you describe the identity of P?
Well, it's all the way down.
One's across the board.
That doesn't exist in S.
Right. S does not have an identity. So it is a subring technically by the definition I gave, but actually S is more than just a subring. Can anybody tell me? Right. Actually, S
And it doesn't have one in it.
is a subring. But more than that, it's an ideal. So I'm gonna take a quick breath from this example here and just to make sure I'm gonna be a good boy and give you the definition of an ideal. Technically, before we go on. So rest stop here so I can give you this. Let R be a ring a non-empty subset in R is said to be an ideal if for all X, Y, and I, and R and R, we have number one, X minus Y is in I. So what does this statement say? What, so X minus Y is in I, what does this statement say? Just one about I itself.
Subgroup, thought of the-
That's right, it's a, yes. Right, I did say non-empty, so it's a subgroup of the ring as an abelian group, right? That's all this is saying. And two, here's the part that sucks, it's a vacuum cleaner. Rx is in. So what this means is, notice that of course this means that, you know, from our definition that I itself is a ring as well. But not only that, it sucks in everything from the ring itself, right? So if I hit something in the I by something in X, it's sucked into the ID, right? And so this is actually this part here. This is the analog of normal subgroup. If we're a fan in group theory of normal subgroups, this is the connection here. By the way, in this definition, what am I assuming? I'm clearly assuming my default that the ring is commutative, right? You can, of course, talk about ideals and rings that are not commutative, but you talk about left ideals, that is, they suck in from the left, right ideals, they suck in from the right, two-sided if they come in from both sides. And when you talk about ideals generated by sets, it gets much more complicated if you don't have an identity in there. So I'm gonna leave that for right now. But let's go back. Now that we've reminded ourselves what an ideal is, let's go back and see how this applies here. What do I need for this my claim to hold up for this to be an ideal? Well, I need it to be an abelian group, so no problemo. We already know the direct sum C2 is a ring, so it's got to be an abelian group, no problem. What about the vacuum cleaner effect? Well, what characterizes this direct sum? It's the fact that it ends in an infinite string of zeros, right? So if you take something that ends in an infinite string of zeros and multiply by anything, it's going to at least end in that original infinite string of zeros, or maybe more zeros, depending on what you multiply by, right? So so is everybody cool with the fact that S is an ideal? Right? Okay. Now here's kind of an interesting thing. I'm going to call this M1. And this ideal will consist actually, this will be better. Okay, I want to consider this idea. Now, let me convince myself that this is an ideal. What do two elements of this have in common? It's just they've got a zero in the first coordinate. Is it clear to you all that if you take any two elements that have zero in the first coordinate, their difference is zero in the first coordinate itself, right? I mean, it certainly gets the vacuum cleaner property, right? Because if I multiply any sequence, anything times this is now going to have a zero in the first coordinate, right? So it's an ideal. Now, again, here's another concept that we haven't, that I think you'll all probably see, we haven't talked about yet formally. There's an adjective that I can stick on this ideal. Do I know what it is? It's a maximal ideal. Okay, so this is actually thing. No other problem. Can anybody justify that?
D mod this ideal is isomorphic to Z2.
That's the slick way to do this, right? So if you all remember, this is a theorem we're going to get to. If you, how can you tell something is maximal ideal, take the ring and mod out by the maximal ideal, and you should get a field if it's a maximal ideal. And one copy of this, Z2 is a field, right? That's one way to do it. I'm going to do it from more of a troglodyte point of view because we haven't got to that theorem yet. So let's suppose that we have a slightly larger ideal. What do I know about my slightly larger ideal?
That has to be one in the first place.
Right, so there's some new element.
Then you construct the identity.
All right. If n contains M1, then 1, A2, A3 is in it. There's some element of this form, right? And now, 0, 1 minus A2, 1 minus A3 is in M, right? Because I've got complete freedom every coordinate except the first. So if I add these two up, I get must be an F, which is contradiction because we were assuming that N was a proper, right? Right. So this truly is max, right? Okay. So there's nothing special, is there, about the fact that I selected the 0 to be in the first coordinate, right? So I can have M2, which is a set of things that look like this, and so forth. And so by letting the nth coordinate be 0, I have defined a countable family of maximal ideals. I agree with that? Okay. Is this it? Is this list an exhaustive list of maximal ideals? Okay. How do you know?
That's contained in any of them.
Right. And of course, there's always the answer, why would the instructor have built up so much excitement and tension if the answer was right? So, theorem that we will get to, and this is again, I think, I love this example because I think it kind of shows how interesting commutative algebra can be. It's kind of a nice motivating. If R is commutative with 1, and I, then R is a proper ideal, then I contains M for some maximal M and R. So this is a more general statement of the one, but maybe a lot of you have heard it this way, but every commutative ring of identity has a maximal ideal. This is kind of a better statement that if you have any ideal, you can actually put it inside a maximal ideal. If we believe this theorem, here's the question. Collection MN cannot be exhaustive. None thing S is an ideal, and none of those maximal ideals contain S, right? Because given any coordinate, so to live in M sub n, you have to have 0 in the nth coordinate, right? Well, look at the element in here that has 1 in the nth coordinate and 0 everywhere else. So this is not contained in any of these maximal ideals. However, the axiom of choice tells us that it is contained in a maximal ideal. Somebody tell me what that maximal ideal looks like. And I'll make you even madder. I suspect that this is contained in uncountably many maximal ideals, but I bet you can't describe what even one of them looks like.
You need choice to construct it.
And this is where the axiom of choice is really speaks out. So suppose you take the direct sum of all this, and suppose you want to start building a maximal ideal that it gets in, right? Well, the first thing you gotta do is make a choice. You have to put an element in this that isn't in the direct sum. So maybe I'll put that one in, right? And now I'll look at the ideal generated by this. Oh, maybe this generates the whole ring. Well, you can prove that this doesn't, right? With just throwing this in. Well, now, is this ideal maximal? I'll let you guys go through this. The answer is no. Now you've got to put something else in. Well, now you can't put in 0, 1, 0, 1, 0, 1, 0, 1, right? So you've got to make some other choice that doesn't make it blow up to the whole ring. And of course, there's lots of choices to be made along the way because there's uncountable many of these things. And every time you make a choice, you eliminate some maximal ideals that you could have put it in. And so it's a mess. I love this example because it really explains. The first time I ever saw this Zorn's limit stuff, I thought about rings like Z, and it's like, why are they proving this? Because after all, I can list the maximal ideals of Z. I can understand what maximal ideals in a polynomial ring look like, right? I know that they're there. This really shows that the axiom of choice is something that was really needed to go the extra mile here. Okay, any questions on that? Any questions? Oh, and here's another one which you might get to as well. Example. Vision room, yes. Actually, you learned that this was a ring in calculus, although I'm sure they never told you the continuous functions make a ring there. But one of the theorems that you learned in calculus is the sum of two continuous functions is continuous, and the product of two continuous functions is continuous, right? You can replace the word continuous with differentiable, various other things. You can just say an arbitrary function. That's a big ring, right? If you don't even demand that it's continuous. You can look at the ring of entire functions on the complex plane. That's actually a ring that's got a lot of interesting structure. I'm gonna leave you today. I'll give you one final definition here. What is? Definition. Let D be a ring such that D minus 0 forms a group under multiplication. Equivalently, for all x non-zero D, 1 over x is in, well, x inverse. We say D is a division. So a division ring is basically if the non-zero elements form a group under multiplication, that is, all non-zero elements are invertible, and a commutative division ring is called a field. Okay. Any questions on that? Any questions? Any questions out there? All right. Well, you all have a good one. Stay dry, I guess, and we'll see you on Friday.